Hi everybody, welcome to week 3 of Chemistry 1. This week we're going to be looking at just a couple of different subjects. First of all, we're going to be looking at phases of matter, then next mixtures, compounds, and substances, and finally we're going to be looking at the physical and chemical properties of matter. We're going to start off with phases. Now, phases are different states that the same kind of matter can exist in. The three that we're most interested in here are solid, liquid, and gas. The first phase of matter we're going to look at here is solid, and this is ice, the solid phase of water. In a solid, the particles of matter are closely packed, and they don't move very much at all. They're chemically bound to each other in some way. Sometimes this takes the form of a crystal lattice, like here in ice. The next phase to talk about is liquid, which we're showing here as regular water. In a liquid, the particles are moving a little faster than in a solid, and they're not really tightly bound to each other. You can't compress a liquid except under very high pressures, so liquids always have the same volume. They'll always flow to take on the exact shape of the container they're in, like the water here is flowing to take on the shape of this glass. I think it looks delicious. I'm going to put some ice in it and have a nice sip. The last phase we're going to talk about in detail today is gas, or water vapor. Now, water vapor, or gas I should say, is really the hottest phase of matter we interact with regularly. And in it, the molecules of a gas are moving much faster than the other phases, and they're not really interacting or bound to each other at all. Unlike a liquid, gas can be compressed easily under pressure, and it easily changes its volume. It spreads out to completely fill any container it's in. So we just saw the three main phases of water, solid, liquid, and gas. The biggest difference here is temperature, with solid being the lowest temperature and gas being the highest. Usually we think about transitions between phases as being caused by temperature, but actually they can be caused by pressure differences too. We're going to talk about that in just a little bit. And technically also there are other phases of matter. The first one we ought to talk about is plasma. Plasma is a very high temperature, high energy phase of matter where all the electrons have left the atoms. The sun is a plasma, or most of it is, and it's mostly hydrogen. And plasma is the final of the four fundamental phases of matter in which most of the universe is existing. So one of those four, solid, liquid, gas, plasma, are the states in which most matter in the universe exists. But there are other stranger phases. One in particular is called the Bose-Einstein condensate, which has really weird properties like slowing light down to the pace of a pretty fast walk. If you want to read more about Bose-Einstein condensates, be prepared to hear about quantum vortices and other strange things. There are even odder phases of matter as well, which we don't want to get into at all because they're extremely rare and difficult to achieve the type of properties you need to get into those phases. The next thing we want to look at is the transitions between all these phases of matter. So what we're seeing here is what's called a phase diagram that shows the four main phases of matter and how you transition between them. Going from a solid up to a liquid here would be called melting. Going the other direction from a liquid to a solid is freezing. Those two we're pretty familiar with, melting and freezing. Similarly, we're also pretty familiar with going from a liquid to a gas, like when we're boiling water, called vaporization. And going from a gas to a liquid, we're somewhat familiar with condensation, is what that's called. It happens pretty normally, like when you have dew outside or something in that realm. Maybe if you're boiling water and it condenses on the top of your pot lid, you get those little beads of liquid water. That's condensation. Some of the others we're not as familiar with, although they do happen, are going straight from solid to gas or gas to solid and skipping liquid entirely. When it goes from solid to a gas, that's called sublimation. Sublimation does happen. You've probably seen it with something like CO2, carbon dioxide, or dry ice turning into sort of fog, how fog machines work. It goes straight from a solid dry ice to a gas, which is that fog. And The other direction, deposition, it's a bit more rare in our everyday lives. But something like frost forming, as an example, goes straight from water vapor in the air to frost on, say, your lawn. Also, soot on a chimney or inside of a chimney is a form of deposition. The soot particles go from a gas, having been burned, straight to being those really black soot particles on the inside of your chimney. The last one up here, that's not super common in our everyday lives, thankfully, is going from a gas up to a plasma. This is when the substance gets so energetic that the electrons leave the atoms. It's called ionization, and everything becomes an ion. In the other way, going from a plasma down to a gas is when it cools down enough that the electrons can go back into the atoms and they become neutral again. It's called deionization or sometimes recombination. Those aren't super common in our everyday lives, but they happen in, say, a place like the sun. So all of this talk brings up the idea of temperature and temperature scales. You're mostly used to hearing about degrees Fahrenheit on weather reports and things like that, but we're not super interested in Fahrenheit in this class. Instead, we're interested in other measurements like degrees Celsius, and one other particular scale as well. This thermometer I have here measures both in Fahrenheit and Celsius, and there's a way to convert between them that we're going to learn later. Degrees Celsius are interesting. They're defined pretty scientifically, with 0 degrees being at the freezing point of water and 100 degrees being at the boiling point, which seems nice and round, whereas Fahrenheit, the freezing of water is 32 degrees and boiling is 212. Not really sure how they decided that. So, the other scale we're interested in is Kelvin, which also has 100 degrees between freezing and boiling of water. But its 0 point is actually quite different. Its 0 point is very low. In fact, 0 Kelvin, and I want to note, we never say 0 degrees Kelvin. For some reason, physicists will make fun of you if you say degrees Kelvin. So we always just say 0 Kelvin is absolute zero. It is the coldest possible temperature in the universe. Even space itself is about 2 or 3 degrees Kelvin. Oh, and there I made the mistake myself. 2 or 3 Kelvin. As a comparison here, my little thermometer tells me that my T is 25.5 degrees Celsius, which is about 290 degrees Kelvin. Oh, I did it again. 290 Kelvin. So we usually think of temperature as the big thing that makes us transition between phases of matter, but actually pressure can do it. Let's look at that. So this is what's called a phase diagram of water. It shows what phase water is in given some temperature on the bottom axis and some pressure on the horizontal or the vertical axis. So far, we've been assuming that the water is at 1 standard atmospheric pressure, that's 1 atm, where below a certain temperature, the temperature of freezing, that's TF, it's a solid. Above TF, but below TB, which is the temperature of boiling, it's a liquid. And then above the boiling temperature, TB, it's a gas. But that's not always true. If we have liquid water, say at whatever temperature this is, and we lower the pressure, it will transition into a gas eventually when it gets to this point. You can see this in vacuum chambers. It's an experiment we'll do when we're back in the classroom. If our vacuum chamber is working, we will keep the water at the same temperature, but we'll lower the atmospheric pressure down to a certain point, and the water will just spontaneously start boiling at a pretty low temperature, usually room temperature, which I think is pretty incredible. Now, this particular phase diagram is very basic. Not only are the axes not labeled, there's a lot more complicated parts and phases water can go into, like this diagram here. Now there's still the stuff we're used to, like liquid, or in this case regular water, and ice, or solid, and even gas. They're calling it vapor here. It's similar to the last diagram we saw, but there's a whole bunch more complexity going on. Mostly in the solid phases. There are a bunch of different types of ice that depend on the temperature, but also the pressure that the water is under. I sub H, ice sub H, or I think H stands for hexagonal, is the regular kind of ice we're used to. If you get it really, really cold, it goes to a different crystalline structure, I sub C, which just has a different structure. And then really, really cold is this orthorhombic ice, yet another different structure. But if you take that same ice and you raise it up to really high temperatures up here, way up here, this part of the diagram, it's under really high pressures and high temperatures, you get to some really strange things. These are all different ice phases, ice 7, 10, 11. They have different properties. They don't really exist in our everyday. We do think that some of the moons of Jupiter and Saturn, the big icy moons of Jupiter and Saturn, have deep in their interiors, under high pressure at high temperature, some of these odd phases of ice are predominantly what's going on. There's even this old science fiction story about Ice 9 here, Ice 9. Although the story was written well before we knew what the properties of Ice 9 were or where it would exist on this table. But the idea of the story was that any other water that Ice 9 came into contact with would instantly turn into Ice 9 itself and make it unusable to humans, meaning there was some sort of an environmental crisis that all the water was going away, and we had to stop the spread of Ice 9. Thankfully, none of that is based anywhere in science or any sort of reality or fact. That is nowhere near what happens. Ice 9 just seems to be another odd, high-temperature phase of ice. Actually, here's a pretty interesting everyday example of that phase diagram we just saw. When we boil water like this, usually we would expect the boiling temperature of water to be 100 degrees Celsius. But up here at altitude in Albuquerque, it's actually slightly less. Because the air pressure is less, it's boiling at around 88 degrees C. Maybe 87, depending on what my kettle says. And of course, as soon as I turn the video down here, it's getting less. This is actually a big problem for mountain climbers on high mountains, because at really high altitudes, that temperature keeps dropping because the air pressure keeps dropping. And of course, it makes it really hard to cook things at lower temperatures. This, however, at 94 degrees C now, is hot enough to make my tea. So let's switch gears just a little bit now to a bit of a different idea, and we're going to compare mixtures, compounds, and elements. So an element is all one type of atom, and that could be even referring to the individual atom itself. As an example, I've got some apples here, so we'll have an apple atom and an orange here, which will be our orange atom. A molecule would be multiple atoms bonded together. That could either be multiple atoms of the same type, so a two-atom molecule, two-apple molecule here, or it could be different types, so an apple-orange molecule. They are, however, bound together chemically. So molecules are some arrangement of multiple atoms and elements all stuck together. Now, a compound is something where you have a substance that are made of maybe different molecules that are mixing together, but it always has the same exact composition no matter how big a sample you have of it. So maybe I have a ratio of 2 apples to 1 orange here in this compound. No matter how much of this compound I have, I'll always have this same ratio of apples to oranges in it. Finally, a mixture is something that has multiple molecules in it. So for example, I'll have an apple-apple molecule and an apple-orange molecule, and they are bound interiorly to each other, to themselves, but not to each other. So they're sort of mixing around just in the same space. If I have a different size sample of this mixture, there could be different proportions of oranges to apples based on how big the sample is and exactly what I sample. In this diagram, you can see the relationships between these different arrangements of matter. For example, over here, if the matter is a pure substance, meaning it has just one type of composition making it up, it can be either an element, which is really just one atom, or one type of atom, or it can be a compound, which is multiple types of atoms, but they're bound together. They're not really separable in normal ways. On the other side, you can have a mixture, which is many different types of atoms, not bound together, but mixed together. And there's 2 types here, the homogeneous and heterogeneous mix. Homogeneous means they're just, on the molecular and very small level, mixed together very well. And you can't really see the difference between them. Whereas heterogeneous here is where there's a clear separation between them. I think this lovely diagram illustrates the differences between elements, compounds, and mixtures very well. Over here it's showing us that an element is just all the same type of atom. So over here we have liquid bromine that's not very organized. Here we have in the middle solid gold, which is really nicely organized and is all the gold atom. And over here we have oxygen gas. Now oxygen gas is a bit interesting because it's two oxygen molecules bound together. We'll talk about why that happens much later in this class. A compound, however, is more than one type of atom, but again, they're bound together, kind of like up here with molecular oxygen. These two oxygen molecules bound together. In this case, it's water, two hydrogens, the little gray guys, and one oxygen, all bound together. Over here we have carbon dioxide gas, which is one carbon, the big black one, and two oxygens, the red ones. And then over here, finally, we have methane gas, which is one carbon and four hydrogens bound to it. So that would be a compound. A mixture is like many compounds all put together. So over here we have table salt dissolved in water, which is the waters we just saw. These big red oxygens and two gray hydrogens mixed together with NaCl, sodium and chlorine, in these yellow and green little squares. Brass here is a combination of, I believe, bronze and something else. I'm not quite sure what. Can't quite remember at this point. But it is a mixture, and it makes a solid. Kind of like gold, it's a solid, but in this case, it's a mixture of different elements. Finally, over here, we have carbon dioxide, CO2, and oxygen. Air would be kind of like this, a lot less carbon dioxide, more oxygen, and actually even more nitrogen. The nitrogen would be, 70-something%, and oxygen would be 20-something%, and then carbon dioxide would be 1% or less of the actual composition of air. But it's all these different molecules of different elements all mixed together, sort of in this big mashup. Here you can see a classic example of a heterogeneous mixture, in this case oil and water, which are well known for not mixing well. In this case, you can see that the mixture is just a bunch of blobs of oil and a bunch of water sort of separately. So they're heterogeneous. You can clearly tell the differences between where one stops and the other begins. Let's finally talk about chemical versus physical changes. Now, physical change is a change in the physical properties of a substance without altering its composition. Something like water freezing, changing phases, air compressing, something like that. There's a lot of different types of physical changes. You're going to be talking about a change in temperature, density, color, hardness, all sorts of things. A chemical change, however, does change the actual makeup of something. A reaction that forms a new chemical substance. Rusting, where iron turns into iron oxide. Or an explosion. Or even regular fire. Or perhaps surprisingly, cooking food, which can change the chemical structure of what you're eating. And that's it for this week, guys. Thank you so much, and I'll see you in class on Zoom this week. Have a good one.